Hello fellow neuroimagers. Today we're going to talk about the 08 lab. This one wasn't too bad in terms of all the code that you had to write on your own, but we'll walk through some of the common gotchas and just show you the workflow, and maybe I'll give you uh, some more details about some of the concepts that we covered. So we'll cd as always into our lab repository, then we'll type Jupyter Notebook to open it. Click on the 08 lab and the experimental design. Alright. Let's see if I can make this bigger. Oh. If I can't, we'll just deal with it like this. Maybe I can make it bigger. There we go. So again, this lab was mostly covering experimental design and how to generate specifically an event-related design in order to optimize our HRF estimation. So how we rank the designs is that we use OPSEC2, and our metric was efficiency. And I said that I was going to give a little bit more of an exposition on what efficiency is, and I found a really good resource to read about efficiency at the Clever Machine WordPress blog. He has written a lot of great resources to understand fMRI analysis and fMRI data processing. So he has thankfully written a post on fMRI experiments, and especially event-related designs. And what we can see from this blog post is, I'm just going to essentially parrot what he said. And the reason that we want more variable onsets as opposed to, so his basic control is just repetitious or periodic onsets of stimuli versus just random onsets of stimuli. But the same philosophy can apply to random versus a more structured, pseudo-random structure of onsets that can even further optimize the variance of the HRF. So the idea is, in a perfectly noiseless situation, when we just look at the HRF being convolved over each of these lines represents a stimulus onset, and the subsequent red lines represent the HRF, or the bold response, that we get as a result of seeing the stimulus. And same idea here for the random presentations. And what we can see is that it's very obvious between these two is that the overall variance of the HRF isn't too much. It's mostly stuck right around these 2 points, and it doesn't deviate from these 2 points. So there's not a lot of variance in the HRF to estimate. Whereas for the random stimuli, there is a drastic amount of variance to estimate the HRF with. So let's see if we can find another picture that maybe makes it more obvious. So I guess we'll stick with this picture. So if you can imagine, if we added noise, so this is just a pure bold response. So if we can imagine if we just added noise to the signal that we've achieved here, it wouldn't take very much signal or very much noise to drown out the variance that we see in the HRF signal that we see here. But we can see when it's random, the amount of noise that we'd need in order to essentially swamp out the variance in the signal that we see, or that we've modeled here, it would take a lot of noise to do so. So we need to add in lots of jagged noise components in order to essentially wash out what would be able to estimate from the variances in the signal. Whereas for this, we wouldn't need to add in, as for when it's periodic, we wouldn't need to add in as many noise components. in order to essentially swamp out the measured signal that we have. So again, this is just periodic versus random, and we can even add in another level of efficiency by looking at what OPSEC does, which is essentially comparing a whole bunch of random designs and seeing which one can have the most variance in the signal, so that one will essentially be the most resistant to the noise and will provide the best signal estimation. And again, this blog post will go into the equations that we'd use to estimate efficiency, and it has links to other blog posts to explain some more of the mathematical aspects of estimating efficiency. Okay. So with that out of the way, let's run some of the code just to make sure that we have everything set up the way that we need to have it set up. So don't need to rerun that. Don't need to rerun that, but for the first problem, I will preemptively copy this code. So Control-C. I don't need to recopy that code. All right. So our first question is if we set the post-stimulus delay, I think that is what it calls, when we set that to between 0 and 4 seconds, how do we predict this to impact the VRF, or inversely the VIF? And VRF is the variance reduction factor, and the VIF is the variance inflation factor. As you can see, the equations that we've defined up here, those are, the VRF is essentially the inverse of the VIF. So, and as a basic explanation of what these terms measure, the VRF or the VIF are essentially measures of collinearity between the conditions that we have. So given, in our example, we have the flanker task with congruent, incongruent, and neutral. So if for a given task, or for a given condition, say congruent, how much can we explain the variance in congruent? So the congruent bold signal across time is our eventual outcome goal. How much of that bold signal could we explain with the incongruent and neutral trial types or conditions? So with VRF, we want this to be a very small number, because then yes, right, let me look at that again. No, we want it to be strike that. We want it to be a larger number. There we go. Sorry, the inverses get me. Because if the r squared is very close to 1, then this is going to be, the 1 minus r squared is going to be a very small number, right? And so r squared is essentially a measurement of the collinearity between our condition of interest, or our current trial type, and the other trial types. So what is the, so again, as I said, how much of the variance in the congruent trial type can be explained by the variance in the neutral and incongruent trial types. And then we'll iterate across the conditions to say how much of the variance in the neutral trial type can be explained by the congruent and incongruent trial types. And so the 1 minus this number, if it's low, is still going to be close to 1, and then if we take the average, we should get a number that is between, well, 1 divided by, yeah, we would want a larger number for this. So the larger number that we can get, that means the smaller the r squareds were. And for the virtual, and for for the variance inflation factor equation, we have just the inverse. So again, it's just one added layer. All that's different is we're taking 1 divided by 1 minus r squared instead of just the 1 minus r squared. So with this, that means we want smaller numbers, and that will indicate a better design, and by better design I mean less collinearity between the trial types. And then how that is very closely related to efficiency, but not quite, because again, efficiency is just worried about the amount of variance that our signal or our conditions can evoke. So we can imagine a scenario where we had low collinearity, but perhaps high, or I guess high collinearity and high and low efficiency. So high collinearity and low efficiency, and that would look, I believe, would look like a block design type task. So there would be not a lot of collinearity between the regressors, as they would be widely separated from each other, but in terms of estimating the href shape, there would also be low efficiency, because all of the stimuli would be shuttled up close together systematically if we were to do like a periodic design block design task, or periodic stimulus onset block design task. Alright, so now that I'm done rambling, we're just going to move on to the actual practice problem. So we're going to think about the variance inflation factors, or the variance reduction factor, where we set the post-stimulus delay window from 0 seconds to 4 seconds after the stimulus, where it was set 0 to 20 seconds after the stimulus. So all this is essentially doing is saying that now we're going to assume that the bold signal after stimulus is now going to only take 4 seconds to resolve instead of 20. So the prediction here should be, we should think that this reduces collinearity between the regressors. Because again, if we think of the regressors like columns of numbers, and the length of the columns of numbers would be as long as there are the number of volumes that we've collected in our experiment. So if each volume represents 2 seconds, if we have a time repetition of 2 seconds, then for 0 to 20, say if we just had a congruent trial start at the 0 point, or as the first volume, then the first 10 volumes would be influenced by the congruent condition. Whereas for if we only imagined it to be 4 seconds, then it would only be the first 2 volumes would be influenced by the congruent condition. And so the impact on collinearity is, imagine back to the 20-second example, if we had a congruent trial for the first at the very beginning, and then we had an incongruent trial, say 3 volumes later, then the bold's influence, or the bold would still be influenced by the processing that occurred during the congruent trial, as well as the incongruent trial, introducing some collinearity between the regressors. Whereas if the post-stimulus delay window was 0 to 4, then if the incongruent trial occurred at the third volume, then the bold response, according to this made-up model, would have already resolved by then, suggesting that there wouldn't be any collinearity between the regressors. So now we're just going to write down the code here that I copied from above, and we're going to change this to 4, and we're going to call this short PSD. And, oh no. Oh yeah, because I need to put that on top. Control X. There we go. And while that's running, we can start to think about what we do for 1B. So we would compare the VRS from 1A. So since we've already defined this function, well, I guess I'll just run it again to make sure that we have actually defined it. There we go. And we don't need to copy that again, per se. So let's do Control C. So yeah, we don't need to copy the function again since it's defined. So I'll just copy the rest of the code here. And instead of sum, we will call this Flinker events short PSD. And that'll be our new sum file, and we will do and yeah, I might as well call everything else the same since we already have the graph for everything else. But if we were actually doing a comparison, we would probably want to rename all the variables so that we could have a better idea to compare them side by side. And by all the variables, I mean we'd want to call this sum file different, this OPSEC info different. Headers would still be the same, but we could also call that something different, df_orig. Yeah, we just name all the variables something different. But since we already have the stuff from above, we can just compare the two. So I think the easiest way is just to look at the graph. So these are the top 5 designs, looking at their variance reduction factor average. But again, remember we are rating the designs based on efficiency, not the variance reduction factor average. So we don't necessarily see monotonic increase in the variance reductor factor average, since that is not the primary metric in which we are organizing the designs. So compare that, see it's around 2. Oh wow, yep, so it's a lot different when we, or it's a lot larger when we shorten up the PSD window, because the collinearity between the regressors is just so much reduced when we assume that the bold response resolves itself in 4 seconds versus 20, which shouldn't be biologically plausible. So this is just an exercise in understanding the variance reduction factor. Same with number 2, we'll just think up of a different experiment. So again, you could write down, we can copy this stuff again. If it'll let me select. No, doesn't do what I wanted. Okay, there we go. So we selected all of it again, and I do the click at the beginning, shift, click at the end, then Control C, Control V. So again, we could change the number of conditions. So maybe I wanted to get rid of neutral, and then I'll just have a total of 80 trials. So then I wouldn't need nearly as many time points because the number of time points is based on, well, the number of stimuli that you have and the minimum amount of null trials that you would need, or null time that you would need. And a good rule of thumb for null time is taking the amount of time that it would take to complete one of your conditions. So let's say congruent. So 40 and including the response time that we would need. Um, each of those congruent trials essentially takes 2 seconds. So we'd take 2 seconds times 40, which would be 80 seconds. And 80 seconds represented in TRs, since they're 2 seconds each, would be 40 volumes. So if we were to do 40 volumes, 80 volumes, 120 volumes, we actually have well over, I guess 240, 80, 120. So that's how many, so that's how many volumes that so 120 is the number of volumes that we would need just to represent, if we just presented the trials one right after the other, no breaks in between. So by adding in this extra time, or these extra volumes, we allow the addition of some rest time in between each trial. I don't want this one to be 20. And so we give ourselves a decent amount of rest time by essentially taking the number of trials that, or the number of volumes that we'd need to represent each of these trials, and then doubling it, and then even adding a little bit more on top. So I guess the minimum that you would need is to take the number of volumes that you would need to model each of your trials and double that. That would be more than adequate, I believe. So again, how I went through that calculation is that I added the 40 trial repetitions, and then each of them is going to take 2 seconds if we include the reaction time, or the amount, the response time that we give them. And since each volume takes 2 seconds to collect, it'll be 1 volume per stimulus, essentially. So 40 volumes would consist of just the congruent stimulus, 40 volumes would consist of the incongruent stimulus, and 40 volumes would consist of the neutral stimulus. And then if we doubled that and just treated all the rest as null time, then we would have additional 120 volumes of breaks in between, or just a little bit of rest in between, to allow to maximize the variance of the HRF randomly distributed. So 240 would be probably the absolute minimum that we would need, and we added a little bit more to beef up our intertrial interval stimulus, so that we allow the HRF, or the hemodynamic bold response, to resolve itself a bit between certain trials, so that we can maximize that variance. Alright, so you can think of different scenarios where you either reduce or increase the number of trials, reduce or increase what conditions you have, and just based on your experimental question, I'm sure that you guys come up with interesting experimental designs. Alright, I think I've droned on long enough for this video. Thank you for listening. Hopefully it answered some questions and got you working and understanding on how to develop a good task event-related design. Alright, and I will stop recording. Thank you for listening.